So, in the previous lectures, we have used the microcanonical ensemble to look at a paramagnet to a ferromagnet transition, and we have also looked at an ideal gas where the Hamiltonian is sum over I pi square over twice m. In the current lecture, what we want to now focus on is something similar, a system of n particles, the Hamiltonian of which is given by C mod pi plus u of qi, where u of qi is equal to 0 for qi greater than equal to 0 less than equal to L, and is equal to infinity otherwise. So essentially what you're looking at is you're looking at a container of volume V is equal to L cube, and the particles are contained within this volume. The dispersion relation, so this particular form of the Hamiltonian, so your total energy is now C times sum over modulus of pi, essentially tells you that you are looking at an ultra-relativistic gas of particles. Here, this was a non-relativistic gas, and we calculated the entropy, the pressure, the equation of state, so on and so forth. Now we want to look at something like this. Now it's illustrative and, well, it's instructive to look at two-particle system first. So let's look at a two-particle system where the total energy is given by C, and C is the velocity of light, so mod p1 plus modulus of p2, in which case if I draw the phase space, the Hamiltonian does not depend on the coordinates, and the total energy expression that we have, which is essentially the isolating integral in this n-particle system, also does not depend on the position, so we only look at P1, P2. Possibilities are P1 plus P2 is going to be E over C. There is a modulus function, so that P1 can take plus and minus values as well. One has P1 minus P2 is equal to E over E by C. And then have minus, again have minus P1 plus P2 is going to be E over C, and finally I have minus P1 minus P2 is going to be E over C. Look at the first equation. So this equation, it clearly tells you that if P2 is equal to 0, P1 is E over C, and similarly if P1 is 0, P2 is going to be E over C. Therefore this represents the line which is essentially like this. Similarly for the second one, I have when P2 is equal to 0, P1 is E over C, and when P1 is equal to 0, P2 is minus E over C, so I have this line. Well, it doesn't, so let's make sure that the arms have equal length, and then we say that this is going to be E over C. Then again, if I look over here, the third equation, which is given over here, when P2 is equal to 0, P1 is minus E over C. So P1 is minus E over C, and so P2 is equal to 0, P1 as minus E over C, and when P1 is equal to 0, P2 as E over C. So that I have this. And finally, for the last one, I have one has to be a little bit more careful. So P1 is minus E over C, which takes you over here, and this is the arm that you are looking at. And finally, for the last one, you will have this arm. So the total number of microstates, omega, for this two-particle system, when the energy is between the greater than equal to 0, less than equal to E, we will just write down over here, even though this is a two-particle system, and we have learned that we can kind of replace the surface area by the volume only in the thermodynamic limit, but let's just consider this for the time being. And we want to know the total number of microstates when the energy of the system lies between 0 and E is essentially the area which is contained in this. And that area I know because this length is a square of length square root 2E over C. So that the total number of microstates is in the phase space, the one which is in the phase space is going to be, so you write as total number of microstates is going to be V square, because there are two particles and they can access the coordinate space, each of them contributing V, and then I have omega of P. So the volume in this momentum space becomes square root 2 E by C whole square, which is going to be twice E by C whole square. Now be careful that I have not put a vector sign over this momenta, therefore I am assuming that this is a one-dimensional system, and if it is a one-dimensional system, one has to say that the coordinates, this quantity volume is no longer there, it is going to be L square. So you replace the volume, so you replace the volume by the dimension of your box along a given direction. So here V therefore goes to L, and you know that for these two particles, so we will say that this quantity now reduces or goes to L square omega P, where omega P is given by E by C whole 2 times E by C whole square. So let's rewrite this in a slightly different way. We will write them as 4 times half E over C whole square. Good. Now we have done it for 2-particle case. Let's look at it for a 3-particle case. For a 3-particle case, I have sum over Pi, which essentially means mod P1 plus mod P2 plus mod P3 is going to be E over C. So that I have a 3-dimensional momentum. So the phase space, the reduced phase space, let's say the reduced phase space is now 3-dimensional because the Hamiltonian does not depend on the coordinates. So we write down the total number of microstates now as L cube, because there are 3 particles and each of which can explore a region of size L times omega p. And here this is a 3-dimensional space, so let's draw it. So I have P1, P2 and P3, and I know that in this 2-dimensional space this is going to be a square of side square root 2 E by C. This momentum P3 also has an upper bound and lower bound of plus minus E over C, and therefore you are effectively looking at a pyramid, a right-angled pyramid, and then you have this. Similarly, this joins this, this one comes over here, you have this one, and you have this one. Well, it doesn't look symmetric in the figure, but you know that both upper half and lower half has equal volumes. Let's calculate the volume of the upper half, and that volume is given by volume of this pyramid in the upper half is now given by your area times of the base times h divided by 3. The area we calculated for this rectangular base was 2 E by C whole square times 1/3 E by C, so that this part becomes 2 by 3 times E by C whole cube. But this is only half the volume, so that the total volume in the momentum space is going to be 2 into 2 by 3 E by C whole cube, which is going to be 4 by 3 E by C whole cube. Now I will multiply this with an additional 2 and bring in a 6 over here, so that I have the form 8 into E by C whole cube divided by 1/6, multiplied by 1/6. So for a 2-dimensional, let's write down this. So omega is L cube, omega P, which is L cube times 8 1/6 into 1/6 E by C whole cube. Now the whole game, or the whole trick, is now to figure out the volume in a hyperdimensional, for a hyperdimensional pyramid. That we can do just by looking at these two examples. So when we had omega P, n is equal to 2, okay, let's write down over here. Omega P, n is equal to 2 was 2 half, we had 2 times E over C whole square, which we could have written as 4 times half E by C whole square, and that is 2 square times 1 over 2 factorial E by C whole square. When omega P n is equal to 3, we have this as 8 into 1 over 6 E by 6 whole cube, which is 2 cube 1 over 3 factorial E by C whole cube. These two expressions clearly give you the hint what the general expression is going to be. So I can write down omega p times n is going to be 2 to the power n 1 over n factorial e over c raised to the power n. And this is the answer that you are looking for. For a hyper n-dimensional, okay, we will not say n-dimensional, let's say for a d-dimensional hyperpyramid, the volume omega is given by r to the power d divided by d factorial, and the hyperpyramid is defined as sum over xi is equal to r, where xi is greater than 0. If you impose this xi greater than 0, then you have this expression. If you say that, look, I do not want to impose, then you will come up with this additional factor of 2. And here the additional factor of 2 comes in because the momenta can be either positive or negative. Therefore, the total number of microstates that are contained for less than equal to E is given by omega, and that answer is going to be L to the power n omega p n, which is going to be L to the power n 2 to the power n 1 over n factorial E by c raised to the power n. Now, we still have not taken into account the indistinguishability of the particles, so that we have omega L to the power n 2 to the power n divided by n factorial, and there is going to be an h to the power n. Essentially that non-dimensionalizes this, because you can see that this is not the thing. This is a dimensionful quantity, and I have again a 1 by n factorial E by c raised to the power n, so that I have 2 to the power n by h to the power n. We will take the h inside, and we will say that this is L to the power n over n factorial square E over hc raised to the power n. So we have this expression now, and if you are doubtful about this, then you know that E is going to be h nu, which is going to be hc over lambda, and this implies that E over hc has a dimension of 1 by L, and exactly you see that this factor, which is 2 to the power n divided by n factorial square L E over hc raised to the power n is dimensionless, as you expect it to be. So the entropy, the direct route is now to the entropy, which is going to be kb ln times omega, and therefore I have kb ln 2 to the power n n factorial square L times E over hc raised to the power n. Let's open the bracket and split everything up. I have n ln 2 plus n ln le over hc minus 2 ln of n factorial, which in the thermodynamic limit I can use the Stirling's approximation for this, which tells me ln n factorial is n ln n minus n, and one has KB n ln2 plus n ln LE over HC minus 2 n ln n plus n. So this is the fundamental relation that we have been trying to emphasize in thermodynamics. So the pressure here is now replaced by del S del L. That should be the pressure. In the when we did thermodynamics, we said that del S del V is equal to P over T, right? But here the volume is replaced by the length L, and del S del L is going to be KB times del del L of n ln L, right? The rest of it does not depend on L, so it is not very significant for us. The derivative is 0, so essentially you have KB n KB over L, so that the pressure P by T is going to be n KB over L, and you have the ideal gas law, which is P by T is going to be rho times KB, or pressure is rho times KBT. The ideal you recovered that very nicely. Del S del E is going to be 1 over T, right? So this implies that del S del E from this expression is KB times del del E of n ln of E. Rest of it doesn't matter because they do not depend on the energy, and which is n KB divided by E. So that I have 1 by T is going to be n KB over E, and this implies E is equal to n KBT. Recall that this was in a 1 dimension. If you had done it for 3 dimension, you would have got the result 3n KBT. So that is precisely the case that you have. This is the dependence of energy of an ultra-relativistic gas. So for thermodynamics, I know that TdS is dE plus P dL, one-dimensional system, therefore I have this. So the two specific heats, this corresponds to the specific heat at constant volume, is going to be del E del T ln n fixed, which is precisely this relation, and is going to be nkB. The specific heat at constant pressure is going to be T del S del T is equal to del E del T Pnn constant plus P del L del T Pnn constant. Did we do something stupid? No, I think this is correct. This quantity is your Cp and this quantity is your nkB, plus if you look at your equation of state, which tells you, the equation of state tells you P times L is going to be nkBT, and since I'm taking the derivative with Pnn held constant, therefore P del L del T P and N constant is going to be N times Kb, so that this term gives you an additional nkB, and therefore the specific heat becomes twice n kb. Please note that this is only for a gas, ultra-relativistic gas in one dimension. This is also ultra-relativistic gas in one dimension. If you are changing the dimension, if you are making this to be in 3 dimension, then this is going to be 3n kb and this is going to be 6n kb. So we now want to take up the last example using our microcanonical ensemble, and that is of a quantum ideal solid. So once again, the picture is that I have a one-dimensional lattice and each of these particles are confined in a harmonic potential which is half m omega square qy square. We will consider the one-dimensional case so that we can treat each of these 3 dimensions independently of each other. Therefore, it suffices to calculate for the one-dimensional case and generalize it for 3 dimension. Now here the energy levels of each of these particles are discrete, and I have the equation epsilon I is going to be Ni plus half h bar omega, so that the total energy is going to be sum over Ni plus half h bar omega. Now let's take specific examples. Consider now two particles which are characterized by n1 and n2. So now we have n1 plus n2 plus half h bar omega plus half h bar omega is equal to the total energy times h bar. This has to be multiplied by h bar omega. And let's say we have E is equal to twice h bar omega. The total energy, I fix it to be twice h bar omega. Then it follows that n1 plus n2 is going to be twice h bar omega minus h bar of omega divided by h bar omega, which is just going to be 1. Is this correct? Sorry, this is correct, but I think we'll take this factor later on. We will just say that it is h bar omega. So now we fix the total energy. E is equal to h bar of omega. This is the total energy of the system. 2 particles, 2 oscillators with a total energy of E equal to h bar omega. And then you immediately see that n1 plus n2 is going to be h bar of omega minus h bar of omega divided by h bar omega is equal to 0. Which essentially means that n1 must be 0, n2 must be 0. No other combinations of n1 and n2 are possible.